Okay, so on your screen now is a good example of a problem which people would traditionally kind of think about in terms of impulse momentum theorem. It's something that technically you could answer using the methods earlier in the course, but it would be a little bit abstract to do so. And it'll be kind of really conceptually elegant if you use an impulse momentum theorem. So we have an egg, and somebody throws an egg at you, okay? And we know intuitively that if somebody throws an egg at you, the right way to catch it is to kind of cradle it softly. If you try to catch the egg just by just catching it, it's going to break. So why does this happen? Why is it that, like, if you drop an egg into a soft cushion, it won't break, but if you drop it into like a hard wooden box, it will break? What's the difference? Because it seems, what's the big deal? So let's say that it takes a force of 200 newtons to crack an egg, which sounds big. That's the number I found online, but anyway, let's just go with it. But anyways, suppose it takes 200 newtons to crack an egg, and let's say somebody throws the egg with the speed 9 meters per second. What's the difference between the soft cushion and the hard wooden box? So here's the impulse momentum based way to think about this. Let's do the box. Oops. Well, okay, we can do it this way. Let's do the box. Come on, box over here, and we'll do the cushion over here. Okay, so the first observation, and the really important observation, is that the delta P is the same in both cases. Delta P is the same whether the object is dropped into the cushion or dropped into the box, because either way, the final momentum is 0, and the initial momentum is going to be 50 grams, which is 0.05 kilograms times 9 meters per second. So all I'm doing here with this delta P is taking m times v final minus m times v initial. So in this case, v final is 0 because the egg is coming to a stop at the end of this process. And v initial is going to be the speed that it's thrown at when it hits the surface, which is 9 meters per second. And that's going to be true whether it hits the box or whether it hits the cushion. So this is exactly the same calculation over here. And the value there is 0.45 minus 0.45, if you like. By the way, the SI unit, kilogram meter per second, no special name. And over here also, minus 0.45 kilogram meter per second. By the way, what's the meaning of the minus sign here? Momentum is a vector. Impulse is also a vector. So if the egg is traveling in this direction, sorry, that is meant to be the velocity. If the egg is traveling in this direction, the positive direction, then the object's change in momentum is going to be in the negative direction. So delta P is going to be this way because you're doing v final is 0. So v final minus v initial. V final is 0, so it's 0 minus the initial velocity. This guy's the initial velocity. So this minus sign here causes the delta P to be in the opposite direction from the initial velocity. So that negative sign is really telling you the sign of the delta P component. Okay, anyways. So the delta P is the same either way. That means we know that delta P equals F delta T. So if delta P is the same in both cases, that means that F delta T is also the same in both cases. Now the difference between the cushion and the box is, for the box, delta T is very small. Because what is delta T? Delta T is the amount of time that the box is exerting a force on the egg to slow it down. So in the case of the box, the impact is very sudden. And because the impact is sudden, it happens very fast. So the impact is fast. That means the delta T is small. The amount of time that it takes for the egg to slow down is very small. For the cushion, on the other hand, the delta T is very large because the cushion slows the egg down gradually over a longer period of time. And you can probably, this is probably starting to make sense now, why the egg breaks in the box and not the cushion, because if you take this process and make it happen more slowly, it kind of makes sense that the egg is less likely to break. But in terms of the math here, if delta P is the same in both cases, F delta T is the same. So if delta T is small, then that means F is going to be large for the box. And over here, F is going to be small. And F, that's the force that the box exerts on the egg, or the force that the cushion exerts on the egg. So basically, because you're stretching out the amount of time that the egg is slowing down for, you can exert a gentle force over a long period of time. And that has the same effect on the egg as exerting a large force very quickly. So, you know, that is really the essence of impulse momentum theorem, is that these two things go hand in hand with each other, that there's basically two ways that you can change the momentum of an object. You can do it either using big forces that happen really fast, in other words, like sudden impacts, or you can do it using small forces that occur over a long period of time. If you do it using small forces that occur over a long period of time, it will usually have kind of less destructive impact on the object. A great example of this that has come up in the news in the last few years is all the discussion about helmets in football and other sports. That, like, you might think, like, a lot of people who, you know, don't have any physics knowledge think, well, you know, when it comes to like a football helmet, why don't they just make it out of some really hard, indestructible material, and then the person's head will be protected? Done, like problem solved. No, that's not the way it works. Because if you make the helmet out of a really hard material, now the person's head is the egg, like in the problem here. If you make the helmet out of a really hard material, what you're going to end up doing with impulse momentum theorem is you're going to end up decreasing the delta T where these impacts happen, which is going to cause the forces on the brain to actually increase, possibly, instead of decrease. And now you've accidentally, you know, by making the helmet harder, you've accidentally made the impacts more sudden and more destructive. So sometimes it actually makes sense to use soft helmets that function more like a cushion and allow the impacts to be stretched out over a period of time. And if you stretch them out, the forces are less sudden. Or, you know, in terms of like different sports techniques, like, you know, you probably remember in the, I think it was Mighty Ducks movie, like they have the part in their training where they pass around eggs and they have to like be able to accept an egg without breaking it. It's the same idea again, where like in a lot of sports technique, in say something like lacrosse is a great example, or hockey is another good example. You want to kind of stretch out your interactions between the bat and the ball, or whatever the case may be, the stick and the ball. Because if you stretch out those interactions, you can, you know, defensively speaking, you can make a smaller force, you know, used so that you can have more control. Or kind of offensively speaking, if you stretch out the time of impact, you can exert that force over a longer period of time, and you'll get more of a change in momentum with the same force. So sometimes it can actually be quite counterintuitive, whether you want something soft or something hard in order to get the effect that you're looking for, in terms of how much force you actually are exerting, or how much force exertion will actually give you the result you're looking for.